This example comes out of section 2.7, implicit differentiation. So far in taking derivatives, every equation we've been given has been in the form y equals, or f of x equals y equals x squared. For example, we've been able to say the derivative of that, dy by dx, is equal to 2x. Or if you prefer, y prime equals 2x. Everything's been solved for y. And in other words, one variable explicitly written in terms of the other. There are some equations, however, that are not like that. We've run into a couple where they've said something like x times y equals 8. Well, in this case, it's fairly simple to solve for y equals 8 over x, or 8x to the minus 1, and say y prime equals negative 8x to the minus 2. It's possible, however, to take the derivative without solving for y, and in some cases it's impossible to solve for y, as I'll show you in a later example. But let's take a look at this. If I took the derivative of everything with respect to x here, I would say, okay, well, let's use my product rule and say I've got x times the derivative of y plus y times the derivative of x, which is just 1, equals the derivative of 8, which is 0. So if I try solving, then I've got xy prime equals negative y, so y prime equals negative y over x. Well, that seems like it's different than what we had above, but if you think about it, if you look at it closely, it's actually not. As we said before, y equals 8 over x. In the case of x times y equals 8, if you put that in here, you've got negative 8 over x, which is negative 8 x to the negative 2, or negative 8 over x squared. It does give us the same derivative. It gives us the same answers. You know, if we were to say at a certain point on this 4 comma 2 is clearly on that graph, this derivative that we got in the first instance would be negative 8 times 4 to the negative 2, which would be negative 8 over 16, negative a half. If I took this derivative that I just had a second ago, where y prime equals negative y over x, I say, well, my slope is going to be my value of y prime, which is going to be negative 2 over 4, which is also negative a half. Implicit differentiation allows you to take the derivative of everything with respect to one of your variables, in this case, to differentiate everything with respect to x, and you end up with a derivative that is just as useful as what we were doing before. Another example of this would be this one. I've got x squared plus y squared equals 25. If you remember a little bit from your math 20 and 30, this is a circle with a radius of 5. It looks something like this. If I don't want to solve for y, in this case it is still theoretically possible, if I differentiate everything with respect to x, I'm going to have 2x plus 2y dy by dx equals 0. This is the trick here, is that every time you differentiate a y term, you get a dy by dx, or if you prefer, 2x plus 2y, y prime equals 0. Every time you differentiate y, you get this y prime term. If I solve for y prime here, I'm going to have 2y, y prime equals negative 2x, so y prime equals negative 2x over 2y, which equals negative x over y. So if they said what's the slope of the tangent at a point on this curve like 3, negative 4, which it does actually go through, 1, 2, 3, 1, 2, 3, 4, is a point on this circle here, I could put that into this derivative and say, oh, the slope of that tangent is going to be negative 3 over negative 4, which is 3/4 or 0.75. Implicit differentiation really uses all the same rules: the chain rule, the product rule, the quotient rule, the power rule, any rule that you've learned so far about differentiating. The only key step is basically right here, realizing when you differentiate, you end up with this y prime or dy by dx term. So we'll try that with one where it's not possible to solve for y in the next example.